Let's get into the first scenario. For the first scenario, we selected a hydraulic door closer as our real-life example because its motion can be accurately represented by a second-order homogeneous differential equation. Okay, when the door is open and released, the spring inside the mechanism generates a restoring force that pulls the door back to its closed position, while the hydraulic fluid provides damping resistance that slows the motion. Since the system involves displacement, velocity, and acceleration, the resulting mathematical model contains the second derivative, making it a second-order differential equation. Then, after the user releases the door, there is no external force acting on the system. The motion is governed only by the spring and damping forces. Therefore, the equation is homogeneous. The model also produces an overdamped response, meaning the door closes smoothly without oscillation or slamming, which reflects the actual behavior of a hydraulic door closer.
For the hydraulic door closer, we first set up the characteristic quadratic equation r squared plus 3r plus 2 equals to 0. Factoring this gives us roots of -1 and -2. Because these roots are real and distinct, our general solution for this overdamped system is st equals to c1e to the power of -t plus c2e to the power of -2t. Next, we apply our initial condition to find the constant. Setting our initial position at 0 equals to 1 gives us C1 equals to 1 minus C2. We then differentiate the position function to find velocity and apply our initial rest condition where x prime 0 equals to 0. Substituting this condition together yield C2 equals to 1 and C1 equals to 2. This gives us our final particular solution st equals to 2e to the power of -t minus e to the power of -2t. Conceptually, as time approaches infinity, both exponential terms decay rapidly towards 0. This proves that our mechanical door closure function perfectly, returning the door to its frame smoothly without overshooting or oscillating.
Have you ever wondered about the physics behind a simple playground swing? In this video, we are going to model a second-order linear non-homogeneous differential equation using a real-life scenario. Imagine a child on a swing that naturally oscillates. To keep the momentum going, a parent applies a periodic pushing force. The external push is modeled as Ft is equal to 5 cos 2t. This gives us our governing differential equation. The second derivative of theta plus 4 theta equals 5 cos 2t. This equation represents the balance between the swing natural motion and the external energy added by the parent. To solve this, we first find the natural response of the swing, how it moves without the parent's push. We do this by setting the right side of our equation to 0 to find the complementary solution. By assuming a solution form of theta is equal to e power of rt, we get the characteristic equation r squared plus 4 is equal to 0. Solving for r gives us imaginary roots, plus or minus 2i. This tells us the natural motion is a periodic wave, represented by our complementary solution, theta ct is equal to c1 cos 2t plus c2 sin 2t. This is the steady natural rhythm of the swing. Now, we need to account for the parent-specific pushing force because the frequency of the push matches the natural frequency of the swing. We are dealing with resonance. To account for this, we use a trial solution multiplied by t. In this specific model, we simplify this to the sine component by applying the product rule to find the first and second derivative and then substituting them back into our original differential equation. We can solve for the constant a. After simplifying, we find that 4a is equal to 5. So, a equals 5 fourths. With both parts of the solution ready, we combine them into one general equation. But what are the values of our constant, C1 and C2? We assume the swing starts from stationary, vertical position, meaning at time 0, both the angle and the velocity are 0. Plugging in our first condition, theta 0 is equal to 0, we find that C1 must be 0. Then by taking the derivative of the general solution and applying our second condition, the velocity at time 0, we find that C2 is also 0. This simplifies our final model significantly. Have it. Our final particular solution for this non-homogeneous system is theta t is equal to 5 over 4t sines 2t. Did you notice the t term in the front? This mathematically shows the effect of resonance. As time increases, the amplitude of the swing grows. This is exactly what happens when a parent perfectly times their pushes. The swing will go higher and higher. It's a perfect example of how calculus describes the world around us.